Hello, everybody. My name is Yuanran Zhu. I am a postdoc from the Scalable Solvers group, working with Dr. Chao Yang and Lin Lin from UC Berkeley. Today, I will talk about a new jigsaw puzzle game we designed for studying quantum many-body systems. So let's begin our talk with a introduction for the motivation of our research. So that is the study for strongly correlated materials. So what are strongly correlated materials and why they're important in modern physics and engineering? Generally speaking, strongly correlated material are not a specific material, but it contains a wide class of compounds that exhibit many interesting and also useful features. These features include metal-to-insulator transitions and high-temperature superconductivity. Here, I just show an example for a typical strongly correlated material and the Meissner effect it exhibits. So basically, as it shown here, you could levitate a very small magnet on the top of a high-temperature superconductor as it showed here. And if you ever watch the movie Avatar, those floating mountain scenes actually got a direct inspiration from this Meissner effect. So the second example is a more recent one. That is the magic angle twisted bilayer graphene. This is a new material that has been a hot topic for a while, which is obtained by putting one layer of graphene on another one and twisted by a small angle. This seemingly simple material actually exhibits many interesting physics. By slightly changing the experimental setting, it actually changed from a metal to an insulator, to a metal to an insulator, and to a superconductor. And the interesting physics of strongly correlated materials exhibit, as well as the technical theoretical difficulty to study the mechanism, has made the study of strongly correlated materials a wide west in modern physics. So if we gain some theoretical or any kind of understanding of the mechanisms for these strongly correlated material, then we'll be able to design, for instance, new transistors, as well as to design superconducting magnets, which are widely used in modern MRI devices. So the goal for our study is to understand how electrons interact. Although these strongly correlated materials are really these molecular structures are rather complicated, but we can understand its interesting physics using some relatively simple schematic model, as I showed here. So what I show is a two-dimensional, three-dimensional structure for its molecular structure. Where because most of the physics that we are interested, such as the conductivity, is pretty much only dependent or determined by the electron's behavior in these materials. So we can propose a rather simple model to understand the dynamic behavior of electrons in the material, and as it is shown here. So you can imagine that you understand the molecular structure of these materials as a two-dimensional or three-dimensional sheet with some topology. As I show here is just a 2D example. So the electrons will basically, according to the fundamental law of quantum mechanics, we know it start to hop between different lattice sites. And if two electrons happen to meet at the same lattice site, as I showed here, then there will be a strong cooling interaction between these two electrons. So this schematic model is already difficult to study. For two reasons. The first one is that you can see the exponential scaling of the problem. That is to say that if you consider a lattice with a green number of sides, then the problem that you aim to solve is actually grows exponentially. So this is the reason why it is very hard to study. And the second one comes from large on-site interaction U here, which is a typical signature for strongly correlated materials. So this will make the normal perturbation analysis fail. So in order to tackle these two theoretical difficulties, the traditional way that we normally do relies on the method called renormalized many-body perturbation theory. Today we'll talk about this a little bit. And also, most importantly, I'm going to introduce our new method, which is called combinatorial Mod theory. So before we talk about our new method, let's do a very brief review of how traditionally we can perform the calculation. So this can be understood as a Feynman's magic. Oh, okay. Well, basically, let us just play a puzzle game. So we all know how puzzles can be played. Okay, this from when we were a kid. So basically, this is specific puzzle is known as a Penrose tiling. And to put the puzzle, it's very simple. So we just gradually assemble these elementary puzzle pieces, as I showed here. Okay, for this pentagon, these stars, so on and so forth. So we can get this puzzle done. However, for this Penrose tiling, this is not the only way we can get this puzzle done. For instance, we can do the following. So we can, by group these 5 elementary puzzle pieces to form a new puzzle, which looks like alien face, and this looks like a flower. With this newly established puzzle, we can also get the exactly same puzzle bound, but this time with much faster rate. So you can see here that this diagram is exactly seen here, but before we play this trick, this puzzle, we need 4 steps to get this done, and this is only 1 step. And this puzzle game interpretation actually is just behind the idea of renormalizing many-body perturbation theory. So in the right-hand side, I just show exactly what we do in physics. So the key physical quantity that we aim to obtain here is the electron self-energy. So this quantity determines how basically the electrons really, whether the material, in essence, it is an insulator or a conductor. So in many-body perturbation theory, the self-energy is calculated using this Taylor series expansion as I show here, where you have a sigma 1 multiplied by u, sigma 2 multiplied by u squared, so on and so forth. So this equation, I didn't explicit to write down what each term really looks like because it's very complicated. And then we can apply this almost like a magic trick here that is basically discovered by Feynman. So what Feynman did is actually, in order to calculate this more conveniently, you can use a graph method to represent this equation. These graphs are known as Feynman diagrams. For instance, you can represent this self-energy using this shaded circle diagram, and this sigma 1 using these 2 diagrams added together, sigma 2 using these diagrams added together. So by applying Feynman's magic trick, we basically transferred a problem which is very complicated analytical problem into a combinatorial problem for graphs. So this is how amazing part of this trick here. And this is not end of story. And most importantly, if you want to perform calculation for strongly correlated material, you need to do a third step, which is a resummation of these diagrams. So basically what you do is you regroup some of the diagrams together, and then build the exact same diagram using a much faster rate. And the logic here is exactly the same as I introduced here using the Jigsaw Puzzle Game. And eventually, after the resummation, we get some workable computational scheme to calculate the self-energy for the electrons and also get the properties for the material we want to study. So this is the idea of what the old method really works. So our method is actually used very similar ideas, but it involves the introduction of new diagrams. So specifically, using our method, which is known as a combinatorial Mod theory, the self-energy for the electron is also calculated using a Taylor series expansion. But as I showed here, but this time something slightly different. This Taylor series expansion is expanded using a different parameter for the system. That is t, actually it's an evolution time. And because this series expansion is different from what we introduced before, you can no longer apply Feynman's trick to calculate or conveniently represent each terms in this series expansion. However, what we have found is that you can develop or discover a new diagrams to represent this series expansion, and that is to use these trees, as I showed here. So you can see that the sigma 0 can be represented as these 2 trees added together. Sigma 1 is represented using these 4 trees together, so on and so forth. So one might ask why we need to use these tree diagrams instead of the traditional method. And we have several reasons behind this construction. So we can clearly see that the tree is actually quite simple when comparing to the Feynman diagrams, because trees are just a bunch of dot points and the lines connecting these dot points, where we can go back and check what the Feynman diagrams really is. Check again. And you can see that it's very complicated because you have straight lines, you have arrows, you have these wiggly lines, right, etc. But the trees are very simple, it's just dot points and the lines. So this simplicity actually brought us many computational advantages. For instance, the immediate thing that we could do with these tree diagrams is that because it has very simple structure, you can translate these tree structures into a symbolic code, and using this symbolic code to automatically generate all these trees that appears in this series expansion. While for the Feynman diagrams, you cannot do so. And secondly, also because the similarity of this tree structure, you can rigorously interpret this resummation procedure that we did before for the trees. For the Feynman diagram, this is actually not an easy task at all, since essentially because of the complicated structure of Feynman diagrams. So in order to get some workable computational scheme, we can do something similar before. That is to do some resummation of these tree diagrams. And this, again, is interpreted by a different puzzle game. So actually, this procedure we need to do is very similar to the previous one. We only need one additional procedure, that is a puzzle decomposition. So the starting point of our theory is a puzzle that is already finished. So what you need to do for the first step is to gradually disassemble these puzzles into these elementary pieces. And then the follow-up procedure is pretty much similar to before. So what we need to do is to gather these elementary puzzle pieces to form some bigger puzzle, and then we do this puzzle resummation. So correspondingly, what we do for the trees is something as follows. So we first perform the tree decomposition. So you can see that in the previous series expansion, we have many trees. And now we just chop them off and decompose them into elementary tree branches, as I show it here. And then we start to regroup these trees to form some new tree. And then we reshuffle the order of the summation and get some workable computational schemes for the self-energy represented using our new theory. And then we can do everything in a more rigorous way, and then we can get the computational done. So basically, this roughly summarized what I need to talk today. So what's new? So basically, we developed a novel diagrammatic method to study the properties of electrons in strongly correlated materials. And we can get some new computational schemes for the electron self-energy by playing some fun puzzle game. And the applications of our new method, we wish to, and also for the next step of our study, that is, we wish to implement and also test the numerical schemes. And also, eventually, we want to understand the mechanism behind, for instance, this high temperature superconductivity and mode transitions, and also the glass transitions. And also, a possible extension of the research is the study of non-equilibrium quantum dynamics. I think that's all for my talk today. And thank you very much for your attention. And now I can take questions.
Thank you, Yuanran, for a wonderful talk. Do we have any questions from the audience?
Yeah, so maybe it's a naive question, but so the sum of your trees is not commutative, right? It depends on the order.
The sum is commutative, but the way you gather them is non-commutative. So I can show it here. For instance, if you graph trees, if you add up two trees together, that is commutative. But if you graph the tree, if you graph trees, for instance, in this order, you get this tree. But then if you graph it differently, you get a different tree. So the grafting of the trees is non-commutative.
Okay.
So you can see I put an arrow here, which means is you only graph it gradually in this way. So here is here, here is here, and here is here. But if you shuffle the order, then you obviously get a different tree.
Indeed. And so for resummation, you need to be very careful about like what you put earlier. And I mean, the order is very important, but only on one side. So only for, not for regrouping on the other side.
Yes,
right.
Yes. When you do the summation, the order is exchangeable. Okay. But when you do the grouping, you cannot. But you can. The good part of the new series, you can do everything using algebraic combinatorics, automatically using code. So that is a good part of the new series.
Okay.
Yeah.
Any other questions from the audience? Okay, so let's thank Yuanran once again for a very nice talk.